in last C.
Number 1?
Yeah.
Okay.
Basically, the first 3 problems are just 3. The 3 problems in the 3 sessions.
No, not in the 3 sessions.
Oh, yeah, okay, in the 2. Yeah.
Okay. We know this formula that T.
Sorry, can you say what the problem
Okay. Yes. Twin brothers are separated at birth. One stays at the sea level, and the other lives at a space station, freely orbiting at radius 20,000 kilometers. Which one will outlive his brother, and by how much? So there is an assumption that they will die together at the same age. Otherwise, there's no point of solving this problem. So I assume that.
Yeah.
And the time. I mean, in a gravitational field, what we know is that 1 plus 5, where there is no gravitational field.
Mm-hmm.
So this is the equation, and let's take it at the surface of the Earth, and the other one is say at the space. So that would be 1 plus, should also be T infinity, and then what I did is that I took the ratio.
So sorry, can I ask, so how should I interpret this formula when you say TR equals 1 plus 5 times T infinity? So if my clock measures like 1 hour, then how much time does pass at infinity? Would it be
Okay.
say I am in some potential there, so phi is negative.
Yes.
Right. So and 1 hour passes according to my clock.
Yes.
How much time? Without looking at the formula, just say whether the time that passes at infinity is going to be longer or shorter than 1 hour.
It will be shorter.
It will be shorter.
Yes.
Okay.
Yes. And we can also calculate from here. It will be a negative quantity, so 1 minus a negative quantity would be less than 1. Then we can calculate from there.
But so imagine, now you are at infinity and I am in some potential there.
Yes.
So my clock passes for 100 years.
Yes.
And I die.
Yes.
And your clock passes for a shorter amount of time.
Yes.
So you won't die.
When you are in the gravitation.
Yes. Okay. If we leave for the same amount of time, yes, I will age less.
Well, let's imagine I'm sending signal. So we're talking about frequencies, right?
Yes.
Yeah, I guess it's all about the minus. So what can I say? I think it's the other way around. If I'm in a potential well, then I experience gravitational redshift. So if I have a clock that ticks with some frequency, according to the observer at infinity, if I send signal, the pulses that I send or the frequency of the things will be, the pulses will be delayed, therefore the frequency will decrease. Right, so if my clock passes for 1 hour, for the observer at infinity, it takes longer to leave that amount of time. So it is the other way around. So I die after you if I'm in the potential there, because my clock measures 100 years, but your clock measures a longer amount of time.
Right. But this is a different scenario, right?
No. It's exactly that. One of the brothers is, well, I mean, you can always take the observer at infinity as a reference point.
Yes.
So compare everyone to the observer. It's exactly what you are doing, actually.
Yes.
So compare everyone to the observer at infinity.
Yes.
So it's the exact same scenario. I first live in the sea level and compare my clock with you, and you are staying at infinity, and then another time I go to the orbit and again compare to it. So why is it a different scenario? In what sense?
Okay, I'm getting confused now. Which was longer, which was shorter? I have to calculate and then check. So, but
no,
yes,
without knowing, it's very easy to screw up the signs if you don't have an idea of which one should live longer and which one should live less. So that's exactly why I'm asking, because I want you to know the answer before calculating.
I see.
Then you can fix the sign. Okay, by continue.
Okay, and this thing was okay. Then we can take the ratio, and what I did is that TR by TS was okay. I'm writing the form of the potential, and it was minus GM by R, and it was 1 minus GM by R plus the radius. It was given 27,000, something was given there. 27,000 kilometers, I guess.
20.
Okay, whatever it was. It was, I mean, this was more than this. So what I did is that, so this number is bigger than this. And so you're decreasing it from minus. So I calculated it, it was around 0.99.
Okay.
So what
Sorry, what is the next digit?
the next digit?
Right.
It was a lot of 9s and then a 5.
But then it is meaningless to say it's 0.99, because what we need is exactly the deviation from 1, right?
Yes. So it was, okay, I just wrote 0.99, but in my calculator I got a few 9s and then there was a 5. This is what I got. So okay, this was the
do you agree that it gives the wrong answer? Because if it is, so imagine the ratio T1, what do you call it, TR, TS. So two possibilities. 1 minus 10 to the minus 2, this is your 0.99.
Yes.
1 minus 10 to the minus 10, this is
Yes.
A lot more nice. Now, if I ask what is delta T, by how much the observer on the Earth outlives the observer on the in the space station, or the other way around. Now I just care about the absolute value. Let's determine the sign later.
Okay.
That is gonna be what? It's gonna be so let's call this 1 minus epsilon.
Yes. Okay.
Right? Delta T is going to be related to epsilon, right?
Yes.
So what is it? Space is TR over TS minus 1 times TS.
Yes.
I just factor that.
Yes. Yes.
But this is going to be an absolute value because I guess we are not sure about the sign yet. So this is going to be epsilon times TS.
Yes.
Right? So TS, say TS is 100 years, something like that.
Yes.
So then it becomes epsilon times 100 years. Now it matters whether epsilon is 10 to the minus 2 or 10 to the minus 10, right? It makes a big difference. Well, big in the, not in the absolute sense, but in the ratio of the two numbers.
Okay, then I made a mistake there, maybe. But
I mean, your calculation shows that the difference
yes.
is very small.
Yes.
So they leave almost the
Same,
amount
yes.
of them. But it doesn't show really what if you truncate these nines
Yes.
without seeing what is the first point at which you deviate from 9, you are not calculating what is the time difference, because that's exactly in this epsilon.
Yes. Okay.
But let me ask you a simpler question. Imagine I have this problem. So suppose, let's forget about gravity. I have just an observer who goes around the circle with velocity v. So, like Alice.
Okay.
Or no, Bob. Alice is always at rest. So Alice sits at the center of the circle at rest, and Bob is going around with velocity v.
Okay.
So can we determine like what is who one lives longer than the other in this scenario? This is just there is no gravity. There is no dilatation.
But there is acceleration.
There is acceleration, or there is also velocity.
There is also velocity.
Yeah.
Have to calculate the Doppler shifts.
Mm-hmm. Yeah.
Yes.
So you can imagine that all this is sending signals to Bob constantly.
Yes.
So she's sending photons, or she has a laser pointer and points it to Bob.
Yes.
Then we can ask what is the frequency of the photon as measured by Bob.
But Alice is giving it in the radial direction, right?
Yeah.
So then do we have to take this change in velocity in subsequent points and take the change in velocity in the I'm thinking like this, that let's say the frequency of this thing is I mean the light from here coming from here is omega here, and then changing its position.
Yeah, but there will be, if I point it correctly, at some point it receives the signal.
Yes.
So at some point there will be, Bob will receive a signal from Alice.
Yes.
And then we are asking what is the frequency of that. It's a well-defined question, right? That's what we always do. Like all of these signals that we are receiving on the Earth from astrophysical objects, they are not always emitted at rest. We are not at rest with respect to them. So there will be some answer to this question. So let's consider the example that we already considered, this constantly accelerating observer. Do you remember? So there was Alice that was sitting at, she was at rest, and then the bulb was accelerating.
Yes.
And she was sending signal.
Yes.
So we were considering photons that are propagating from Alice to bulb, and we were asking what is the redshift of those photons.
Yes.
So would it matter that it is accelerating for us? But imagine I received a signal at some point. Then I have velocity v. Then what would be? Okay, let's assume that it's moving with constant velocity.
Yes.
Then we can determine what is
yes.
there. Okay, so what would be that? So imagine there is somebody with constant velocity.
Yes, but it's perpendicular to the light velocity.
Uh-huh.
That is where my confusion is right now. That I mean, the Doppler shift happens if you have relative velocity in the direction of the light, right? In the perpendicular direction.
Not necessarily. You are saying that omega b will be equal to omega a. I mean, there will be some answer for an omega b.
Yes.
So say what is omega b?
Yes, I guess I'm not sure, but I guess it should be omega a is equal to omega b.
But how do we determine it? We go to a rest frame of Bob, and we have a photon which has a four momentum.
Right.
That was the procedure for measuring, determining frequency as seen by an observer. So we are saying the light ray has some four momentum, k mu.
Yes.
So in the Alice frame, that k mu is what? Is omega times 1 in t direction and 1 in y direction, or minus y direction.
Yes.
Now we go to the rest frame of Bob.
Yes.
That 4 vector has changes, right?
Yes.
Because it's a different inertial frame.
Yes.
It's still null vector, but it's a different. Then we look at the zeros component of that, it will be omega Bob, right?
Right.
So it's just a matter of doing
a Lorentz transformation.
A Lorentz transformation on the k mu.
Yes. But how would I do the Lorentz transformation?
But don't say that you don't remember Lorentz transformation.
No, I'm not saying that.
So let's try to do that. K mu is a vector that moves in the y direction. So
okay.
We have K mu, which is omega.
K mu is
omega 0 and omega.
Yes.
And then Bob is moving along x direction with velocity v.
Oh, yes.
So So we just want to do a Lorentz transformation of this four
Yes.
vector
And it will
to a
turn
new
into
frame.
the direction.
Yeah.
Then it will be gamma.
Can we do component by component just for simplicity?
Okay.
Like k, what will be k prime 0?
K prime 0 will be gamma k 0 minus gamma beta.
So say, let's even determine already what is k prime 0 because then we are almost done.
Yes. Then
What
this,
was the redshift
K,
we can determine
this is
just
0.
by looking at frequency.
This term is 0, so this is.
Okay, so now tell me what is omega b.
That's gamma times v, but I'm not sure. I'm having the confusion with the relative velocity because this gamma factor is this, right?
Uh-huh.
And I'm confused about this.
And
V.
why?
Because this is what we know, that this is the relative velocity between the two frames, right? We are
Uh-huh.
hanging, and here I'm not sure about the relative velocity.
Well, why is it not v?
But it's changing the direction every time.
At the moment of detection in this v, right?
Right. Yes. Okay. Then it's just gamma times omega. Yes. And
So if I had some
yes,
instantaneously
I can calculate
frame,
the x frame, x axis, right? And then that frame, then the velocity is v. Okay. Now I get it. Yes. Then this is my answer. The new omega would be gamma times.
okay, so which one is larger?
This number is greater than 1.
Uh-huh.
So gamma times omega a was equal to omega b.
Mm-hmm.
And you're multiplying something greater than 1, then this is larger. Omega b.
Okay. Alright, so if omega a is measuring the clock of Alice,
Yes.
what Bob sees is that the clock of Alice is
ticking faster. Yes.
So Bob outlives Alice.
Yes.
Okay. So this is a step 1 in solving this problem because we are having someone who is orbiting the Earth. So there will be some just kinematic Doppler shift. Even if there was no gravitation, there will be this effect.
Yes.
And now we can ask the second question.
The gravitational.
Yeah, now let's imagine somebody is at the Earth level and somebody is in the space,
yes,
but at fixed, it's not rotating. So he has some spaceship. He has his engines on, so let's consider now the following. So this was problem number 1A. So let's say omega b was gamma omega a. So we can erase. So let's ask another question. This is a question number 2. Maybe we can already solve question number 2 as some help for question number 1. So imagine there are 2 observers. Now there is Alice and there is Bob, and they are sitting at 2 different potentials. So this is phi A, this is phi B. So they are in a room. And then we want to send signals from Alice to Bob and ask what is omega B in terms of omega A.
Yes.
So I guess this is similar to what you were doing.
Yes. That was the ratio between the one plus the potentials. Yes.
Now the only thing that we need to do is to understand how the signs work.
Yes.
Which is the tricky part, I guess. So what is the so let us remember, how do we determine omega for somebody who is sitting in some potential phi? We said that if we consider some little clocks that work in here, we have a coupling of, or any massive object is coupled through this interaction. We have this sigma square root of minus eta mu nu x dot mu times 1 plus phi. And then we said that if we talk about some x tilde mu, which is 1 plus phi times x mu, then everything is as if the size of the clock is much smaller than the
change of the field.
The scale of variations, then with this redefinition, we get basically the same physics, but the same physics in terms of tilde variables.
Yeah.
So if we have some internal frequency omega 0, that has to be related to delta of x tilde 0. So this omega 0 is basically omega infinity. Well, I think notations are very confusing here, so that's, I don't know what to call it. But I guess already from here, what we see is that if I have some time passes in the frame of this observer, delta x tilde 0, we have to have a longer time that passes at infinity. So this x0 is the time that is measured at infinity, and this is the time that is measured by I. So let's say there is Charlie at a point when phi is equal to 0.
Yeah.
So this delta x0 is the time that is measured by Charlie, and this delta x tilde is the time that is measured by Alice.
Yeah.
So then we can determine, and this phi is the potential of Alice, right?
Yes. Then this thing would be the same for both of the observers. This divided by this thing.
Right, then
for the Bob.
except that there is phi b for Bob.
Yes.
Yes. And now this equation tells me, so now if Alice's clock measure 1 hour, Charlie's clock measure shorter or longer than 1 hour?
Because this is negative, so this is less than 1. So if you multiply this, if you divide this with something less than 1, it will be longer.
Right. So Charlie's clock measure longer. So
Yes.
Alice lives longer than Charlie.
Yes.
Bob also lives longer than Charlie because phi b is also negative.
Yes.
Now the question is what is the ratio of Alice time and Bob's time? So that would be, I think, what you were calculating, right?
Yes.
Okay, now we should put them together, right?
As a product, right?
There is this effect for Alice, the same effect, similar effect for Bob, and also the fact that Bob is rotating
So
around the
there will be a
Earth.
transformation.
Yeah.
Okay.
Okay, so we want to put them together.
Okay, okay. Then
there is also a little dynamics problem of determining V of Bob in terms of the radius of the orbit, because it's a circular orbit with
yes.
some fixed radius.
Yes.
So V will be related to other
The
parameters of the problem.
Yes.
Okay, go ahead.
Okay, then this ratio is equal divided by it's proportional, so that should be 1 minus Alice was in Earth, right?
Yeah.
So it should be just R, and it should be R plus something.
Let's call it RB, RA and RB.
Okay. Yes, now what do I have to do?
But these effects are all small, so we can just put them together. In a sense that you can just multiply. So there is also a factor of gamma.
Yes.
That should be multiplied.
Yeah, so
also.
we should just omega b by omega a. So this is just equal to this, and then we should multiply by gamma.
Well, I think we should decide whether it should be multiplied or divided by gamma. But that we can determine again by asking who should outlive who, whose clock should work faster, right?
Yes.
So we already understood if we forget about gravity, how should it work? If Alice measures 1 hour, Bob measures shorter than 1 hour, right?
Yes.
So then we know whether gamma should be in the numerator or denominator.
And they're getting confused again. Okay. Wait, omega b was higher because it was greater than 1. So omega b was greater than omega a. So his clock runs faster, and so the time measured by him will be smaller than time measured by him, right? I get confused with this thing.
Yeah, I agree that it's a bit confusing, but we should get used to it. You should get confused enough to then learn how to determine the answer. So
yes.
We decided there that if I'm Alice and I'm sending signals,
yes,
the signals will be what? Will be red shifted or blue shifted in the buffer. So omega A is measuring the clock of Alice.
Right.
So Bob is the omega B was the photons that Alice is sending, but measured by Bob.
Yes.
So what Bob sees is that the Alice's clock is running faster.
Yes.
Therefore, if Alice measures 1 hour,
yes, it will measure more.
Bob will measure shorter than that because Alice's clock is running fast.
Okay.
But think about the twin paradox. If this Bob is the one who is moving with some velocity, so he should stay younger.
Yes.
While Alice is at rest.
Yes.
So Alice ages fast.
Are you serious? Fast, yes. So there should be more. This term, I mean, then we should multiply by gamma.
Okay.
Because this is more than this.
Okay. Yeah.
Right.
Okay, so all that we need to know now is to relate gamma to RB and RA and the radius of
Yes,
the...
yes.
Okay.
Okay. Should I do that?
Yeah.
Okay. Velocity with radius. R plus H, let me call this. And then these two cancels out, and we can find.
Sorry, wait. What
I was equating the force.
Why is it that why do you...
Oh. Oh, I'm sorry. Okay, I was just equating the force, the centripetal force, for the. I'm just trying to velocity as a function of r.
Yeah, but what is the right hand side? Is that the Newton's force?
Yes.
But why do you have two different radii?
Yes.
I thought we just say R.
Oh, okay.
Yes, so from here we can calculate v as a function of r. The rest are constants. The mass and the gravitational
No,
constant.
but can you do it?
Okay, velocity is
You can call it RB.
okay. System.
Okay, so then what would be the answer? I mean, the answer is gonna look nice. That's why I'm
Okay.
forcing you to do it.
Then let me calculate gamma.
The square root is on everything.
1 minus gm by
Wait.
The square root in everything. Because you cancel the R plus H and the square.
Square over R.
In the first equation.
where?
R,
Here?
yes,
Yes.
and the square.
R plus H goes with this square.
With the square?
Yes.
No.
With the other.
Where you're...
Yes, I mean this cancels this square.
Yeah,
So the square root will be on everything.
Oh. I'm making some stupid mistakes, I don't know why.
You take the square.
Okay, take the square, then I'll have this.
Okay, now this ratio is small, right?
Yes, then.
Okay, so let's plug it there and then expand to first order in Gm over R.
Okay.
Expand everything to first order in Gm over R.
And so it's multiplied, it's minus 3 by 2. Times, and this is minus 3 by 2, so that's 1 minus 3 by 2 gm over.
In the denominator.
Yes, because if I multiply these two, it will be 1 minus to the power minus 3 by 2, and I expanded it. And
So plus,
first.
so plus, because you have minus minus. You have minus gm and you have minus 3 half.
Yes.
Okay.
And I multiply, it will be 1 plus minus GM by RA and plus 3 by 2 GM by RB. I'm ignoring the other term, this multiplication, because that's going to be in first order.
Okay.
So this is that.
So does anyone know what would this be? Did anyone get this ratio? What would be the number? No. Okay, I got. Well, this is. Thank you.
Can I go?
Yes. So this is what 1 minus GM over RA. 1 minus 3 over 2 RA over RB.
Yes.
Oh, I guess I was taking RB to be this 20,000 kilometers, so I was assuming that it's at radius.
From the
Isn't
center?
it? Yeah.
200,000.
So with that, I got what? 10 to the.
Okay.
It wasn't that negligible actually. So, so what are we measuring? This is TA divided by TB. And okay, so first of all, this ratio is something of order of 0.5 according to my calculation. And then this number, remember there is a CF squared here.
Yeah.
When you are plugging numbers.
Yes.
And that was something of order 7 times 10 to the minus 8. So I got 1 minus 3.5 times 10 to the minus 8. So what it shows is that this is, first of all, this is less than 1. Right? So if Alice lives for 100 years, Bob lives for a bit longer than 100 years. So Bob outlives Alice. And then we can determine by how much, by this much times 100 years. So delta T AB or BA, which is TB minus TA, is something over this number times TB, which if I take it to be 100 years, then becomes something like 100 seconds.
What?
So it's not that negligible.
Yeah,
It's huge.
that's long. It's a lot.
Maybe I'm screwed up some calculation. That's what I got.
We didn't even do the calculation.
Any questions?
Is this okay, just multiplying by gamma here?
Here?
Yes. Because we just arbitrarily put the gamma, put together the two effects.
Well, because you are linearizing in GM over R. That's why it's okay to do it. Because this gamma was also, the deviation of gamma from 1 was also GM over R.
It's not here. It's done.
Hello?
Happy question sheet.
Question? Yes, sir. I just-
Okay. What's the temperature difference in a thermodynamical equilibrium at room temperature between the floor and the ceiling, 3 meters high room due to gravity? Okay. This is floor, and this is ceiling, and we have a gas in here. So the question is, what is the temperature in here? The difference in the temperature. So I thought about it like a redshift problem also.
Mm-hmm.
So again, using the same formula, I use the I'm not gonna go up there. So I use the reference point, which is here, to be the infinity, and omega infinity would be equal to 1 plus pi omega, but when we measure in the floor. So if I'm measuring from the floor, omega infinity would be 1 plus pi.
Sorry, can I again?
Yes.
So can we determine which part would be cooler, just without writing formula?
Yes, wait a minute. Yeah, the floor would be hotter.
The floor will be hotter. Why?
Well, because of I'm not sure if you want to. Pi on the floor is bigger than the one on the ceiling. Because of
Bigger or it's absolute value?
Yeah, it's absolute
it's
value.
Negative.
Yes.
Okay.
So it's if I'm measuring at the floor, omega floor, yes.
Sorry, but you were going to explain why it's hotter in the floor without using the formula.
Okay.
So let's do the following thought experiment.
Yes.
Imagine I have some transition line. So one way of measuring the temperature is to see what transition lines are being excited at that temperature.
Okay.
Right? So imagine I have some transition line, or so many transition lines. So there is one of them which is being excited at the bottom of the room, and it sends a photon.
Yes.
And then the photons goes up, and it has to excite some other transition line. So we can ask whether we know that the highest is the energy difference of transition lines, the higher is the temperature, right? The higher, which is like as I go to very high temperatures, I can excite larger, more high energy transitions that corresponds to higher frequency photon.
Yes.
Right, this is from quantum mechanics.
Exactly. But
So can we now say which part should be hotter, bottom or the top, by this thought experiment? Like which are the transition lines near the floor, are those more energetic or the ones which are near the ceiling, and why?
Okay. It depends on the photon itself. So if it's red shifted or blue shifted, yes. But I'm trying to think about the photons themselves. This is what I came up with. So the photons that comes from the the floor to the ceiling would be red shifted, and from the ceiling to the floor would be blue shifted. So the floor, the temperature, the gas on the floor will have more energy or kinetic energy, which is temperature, because of the blue shifting of the photons.
Okay. Yeah, that's all right. There is a very easy way to think about it. There is a potential difference between floor and the ceiling. So the photon has to climb up some potential well, and it loses energy.
Yes.
So as the photon goes from the floor to the ceiling, it gets redshifted.
Yes.
It becomes cold.
Okay.
Now we know the sign.
Yeah, and ceiling. W. Oh, sorry, this is infinity. Ceiling. So it's just a matter. T floor, T ceiling, T. Which is 1 minus G M over R floor over 1 minus G M over R ceiling. Yes.
Well, this phi is something small, right? Like in the previous example, it was what, 10 to the minus 8 or something.
This? 3.5
It's something tiny.
Oh, yes.
Right?
Yes.
So let's linearize.
Yeah, I'm going to linearize the what is it? Over R floor multiplied by 1 plus G M over R ceiling. And 1 minus G M over R floor plus G M over R ceiling. Over R floor minus ceiling. I didn't put the numbers.
Okay, you don't need to put the numbers at home. You can do it right now on the board.
Oh.
Except that, can you linearize it already at the first level, like when you write it in terms of phi f and phi s?
Here?
Yes. So we know that phi f and phi s are both small. So
yes.
what is the result then?
it will be
and you can continue to write it as
over TS.
well, we want to linearize it in terms of phi.
Yes, okay, so 1 plus phi f minus phi s. What?
And
Okay.
so this is what TF over TS.
Yes, this is TF.
So we decided TF over TS
It's
is larger than 1,
plus
right?
epsilon.
So is phi f minus phi s larger than 1 or smaller than 1?
It would be epsilon, be less, smaller than 1.
So are you saying that TF is less than
Oh,
TH? Sorry, by 1 I meant 0. Is phi f minus phi s positive or negative? That's what we want to see, if epsilon is positive or negative.
TF over TS. It would be positive. If TF over TS would be positive. So T floor.
But phi f and phi s are both negative, right?
Ah, yes. Sorry, so this is negative quantity. This is so it's 1 minus something. And
Negative.
So this one is bigger than this. The floor, the phi floor is bigger than the phi ceiling.
Is it bigger or smaller?
Well, the
absolute value.
Yeah, so phi value is bigger than phi s.
So 1 plus phi f minus phi s is less than 1 or larger than 1?
I'm confused about the 1 though. So the value of phi f, because it's a minus, so this one, this thing is negative in here. So 1 minus something would be the TF over TS.
So it's less than 1.
What? Yeah, it's less than 1.
Didn't we decide that TF over TS is larger than 1?
Yes, it's just yeah, this value is really small. It's like something to the minus
was
e.
there in the
What?
first equation.
What?
The first equation.
Yes.
The other way around. It's the inverse of that. 1 plus phi s divided by 1 plus.
Right.
Yeah. Then you'll have this.
So you're saying that I made a mistake here?
Yeah.
The temperature is something that is like frequency.
Yes, sir.
So look at your own equations. Frequency times 1 plus f is constant. Frequency times 1 plus phi is a constant.
It's inversely proportional.
Therefore, temperature times 1 plus phi should be constant. Like Tf times 1 plus phi f should be equal to Ts 1 plus phi.
It's not
However, the whole point of asking whether floor is hotter than the ceiling is to get the sign correct. So you can just write the correct equation knowing that the answer has to be Tf over Ts
here,
larger
not
than
in
1.
the problem before.
So I just also here. So it's positive, and this is bigger than.
Okay.
Yeah, so it's
So now we want to plug in numbers.
Okay.
Can we plug in numbers?
Yes, I think so.
Without 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 using the radius of the Earth, because we don't need to know the radius of the Earth. It's just a 3-meter high room.
Yes, I know. It's no.
R plus 3.
Yes,
Denominator.
So what is pi s minus pi f? It's just the potential difference
Between the ceiling and the floor.
So imagine I have an object and I want to move it from the floor to the ceiling. How much work should I do?
The work depends on the path from the floor to the ceiling. The 3 meters. Yes.
Like the gravitational force in the room is almost constant, yes. Right? The constant of acceleration is g, per 10 meters per second square. So what is the force?
The mass of the g.
Right. So now what would be the potential difference if I move something with
the mass with g multiplied by the h, which is the 3 meters.
Okay. So that's the energy. The potential difference is the energy divided by the mass. So it will be just
G times 3. G times
G with h?
3, yes.
3, yes.
Yeah, let's just write the formula in terms of h. Imagine the height is h.
Okay.
First write in terms of the parametric equation. So g times h.
G times h.
So that's the potential difference.
Yes.
So we want to calculate that.
I don't remember what is G though. It's a constant. G times h is constant. It's 3 meters times 10.
Okay. So now you can calculate.
I'm not sure what to do right now.
Well, let's go back to our formula. So we say TF over TS is 1 plus delta phi. So we want to calculate delta phi, the potential difference between the ceiling and the floor. The potential difference between ceiling and the floor is given the height of the room is something that we can calculate.
Yes. -1.
Where does 1 come from?
Oh no, that's it. I think we should it.
Okay. So what is its numerical value?
This thing, it's almost 30. What?
the dimension of G times H?
Plus
Wait.
G, what is the dimension of G?
and GH
Wait. The per second square.
so it has to be a number.
Multiplied by H meter
No,
square. This is
10
the,
times H.
And the velocity.
is 10 meters.
so it's meter per second squared, which is V squared.
So we want to add it to
Yeah.
1, so it should
So we
be.
have to divide by C squared. Well, 3 plus 8 is 5 squared. So it's 1 plus 3 times 10 to the 8 16th minus 15. Something like that. Okay.
Okay, so it's the difference is like, say if the temperature is room temperature, then what will be T?
Yes, if room temperature would be like 24 Celsius, right?
Uh-huh.
Yeah, I think so. So this is
So let's calculate delta T.
okay.
What will be delta T
Delta
at room temperature?
T floor ceiling, which is ceiling. T floor ceiling. T ceiling. Okay, so this is plus 15 T ceiling, which is 24 multiplied by this number.
So say the room is very cold. Imagine
Yeah,
it's
the
0
difference.
Celsius.
Okay.
Would you get 0?
Oh.
Say it is minus 5 if you are in a fridge.
Okay.
Does your conclusion change about the fact that ceiling has to be colder than the floor?
The scaling.
Oh.
The absolute temperature. Minus 5 degrees Celsius. And what has
The thought experiment tells us that it's the same thing. So ceiling, the floor should be hotter than the ceiling in the fridge or not. So there's something.
Well, we should determine what is the in what units we are measuring temperature.
Okay, so yeah, it's Kelvin.
There is one unit of measurement which has a preferred 0.
Yeah.
And that's Kelvin.
Yes, because we can't reach the 0.
Then the ratios will change.
Yes. So I should change this to the.
So room temperature is like 300
Kelvin, yes. Whatever. So yes, and we can't reach the 0 from. In theory, we can, but in the Kelvin, we can't reach 0, right? So this formula is valid, I think.
So what is the number?
Okay, so it's 13 Kelvin.
So minus 13 Kelvin. Okay. Let's see what I have the same number. Thank you. to problem 5.
We were waiting for 3.
Gen 3?
You want to do 3 by itself.
Just
You want
a
this?
few lines, see if we can do it.
Yeah, okay.
So why is it so funny to jump to problem 5? You all know the answer of problem 5.
We couldn't do 3 and 4.
3 and 4.
3 and 4 was bad.
So, to start, we have to find the QIJs.
Or can you first say what the problem is?
Estimate how long it would take the Earth to fall down on the Sun due to emission of gravitational waves in scalar gravity. So, we need to first find what is QIJ. X dx times xj.
So why don't you calculate the monopole and dipole?
In the monopole represents the total mass of the system, and since the system is the masses don't change, then the time dependent, at least the time derivatives of the monopole will be 0. And in the dipole, since the dipole in this case represents the momentum, the center of mass, the time derivative of the center of mass. The second time derivative of the center of mass will be 0.
Of the dipole.
Of the dipole.
Yeah, in fact, I think the dipole itself will be 0 in the center of mass.
Minus r squared.
Although there is some question that might be a bit confusing. I mean, you don't need to answer it now, but just one thing to think about. Is dipole 0 to all orders? To leading order in non-relativistic approximation, it is obviously 0 in the center of mass, because it just reduces to the momentum of the system, total momentum in the center of mass, which is 0. But if I go beyond the leading order in V squared, then it's a little bit, it's not that obvious whether it has to be 0.
The Earth, the difference between the radius vector of our Earth and our Sun will be the separation vector of our Sun. Note that our Earth, the Sun and the Earth have different masses. So if we first visualize the orbit in the center of mass, and this is the center mass, which I set to 0. In this orbit, in this case, we make a small approximation that the Earth and the Sun rotate as circular orbits up about the center of mass.
Isn't the center of mass almost at the center of the Sun?
Yeah.
Okay. That simplifies
Yeah.
the calculation.
So we then calculate
What would be the distance of the center of mass compared to the center of the sun?
Yeah. So, 150 million kilometers. 69.
Sorry, let me understand your notation.
Um,
What is big R?
Big R is the separation vector.
Big R is the separation, and this formula is the distance of the center of mass from the center of the sun.
Yeah.
Okay, but even before plugging the, say I don't know R. As a ratio of the R, that would be something over the ME over MS times R.
Yes.
Which is like 10 to the minus 6.
Yes, 10 to the minus 6.
Okay, so let's assume that is 0. Because, so the question just asks you to estimate. When you ask to estimate, it means that you don't need to care about order 1 numerical coefficients. We just want to see what is the order of magnitude of the answer.
Okay. So we will find that Q XX will be equivalent to 3 3 halves ME R squared 1 plus cosine 2 omega t. Q by y will be somewhat the same. We have R squared 1 minus cosine 2 omega t, and qxy will be 1 minus 3 me r squared over 2 sine 2 omega t. Now if we take the change in the energy, the power loss is approximately negative G, or 270 times E QIJ over dt cube squared. Find that this is actually equal to dt squared. Find that this will be equal to a piece. I'm skipping ahead. Piece in my calculation. Minus 16 e to the 4th ME plus MS.
Which is almost MS.
M. It's ME squared MS cube over 15 R to the 5th, C to the 5th. Now E, the energy for a bound systems, negative 1/2 G ME MS 1/2 over R. We then arrive at a formula for dr over dt, which is equivalent to negative 32 t to the cube ms squared me, or 15 c to the fifth r cubed, integrating from big R0 we get 15 c to the fifth r to the fourth 128 8 cubed ms squared me, which is approximately equal to 6.438 times 10 to the 23 years.
Can you compare it with the age of the universe? Do you know how long?
It's 13 billion
13 billion years. So it's like 13 times 10 to the 9. Yeah. So it's much, much longer than the age of the universe. Okay, thank you.
I have a question with this one.
Yeah.
To compute that, you take the third derivative of q,
Yes.
but you don't take into account the terms with r dot, because q also has terms with r. And which is the same thing we did in class, and but precisely we want to calculate the change in r, so should we also take into account the terms with r dot and then solve the full differential equation?
No. Because why do we have non-zero r dot? You are saying you are worried about r dot because due to the emission there will be some change in the radius, right? But the emission itself is very very small, right? So there will be some contribution to this Q triple dot that is zeroth order contribution. So we will have some Q triple dot Ij, even if we assume that there is no gravitational emission. Then once we calculate that, so we are doing perturbations. The rate that we are getting for the emission is an extremely small value. So what we are doing is that we are assuming first that we have a stable orbit. So if r doesn't change, we calculate the emission. From that emission we get some change in the energy. Then from that we calculate r dot, and then now if we want we can improve this result by including the r dots. But that would be a first order correction, which is already proportional to the emission that we consider. So if I include that r dot in the result, then I get something which is so what would be the parameter that controls this? It will essentially be the square of whatever small number that we have here for the emission. So it's the leading answer in the perturbation theory.
seems like the only reason this is, so we found that this is small, but without taking our dots into account. But how do we know that if we take them into account, it will still be, how do we know the R dots are of first order, not of zeroth order as well?
So let's see, what are we? Let's try to understand what is the parameter. So when we are taking dots, we are ignoring R dot over R compared to the frequency. So we are assuming that this holds. Now you are asking, how do we know that this result? How do we know that R dot over R is less than omega? Well, one justification can always be the posteriori justification.
But that's my question. We got that result after assuming that it was small, but maybe if you don't assume it from the beginning, like if you take the full thing into account, maybe it won't be. I don't see why we're allowed to use the posteriori justification without doing the full calculation.
Okay, so imagine I keep those terms. So there will be Q triple dot. Q triple dot will be Q triple dot, what I call Q triple dot 0 times 1 plus R dot over R omega correction, or the R dot over R omega correction, right? Now let's go and calculate calculate the energy loss or power loss from here. This will be equal to, so dE dt of your orbit will be minus that. And this, on the other hand, so this will be some relation. dE over dt is related to R dot itself. So this is something proportional to R dot, and that will be proportional to the square of this quantity. In particular, it will contain the square of this thing. Now the question is that can this R dot over R omega be large? So we know that we started from R dot over R omega is equal to 0 in our whole calculation. It was a circular orbit to begin with. So if I set it to 0 at the beginning, then I will get some answer for R dot. And then I can see that that answer is going to satisfy the condition that R dot over R omega is very small. Or if you start from any number for which this ratio is small, you can keep it through the calculation and see that the final answer remains small. Essentially because this overall coefficient will be tiny. Right, this is some correction which is r dot over r omega to what we already calculated. So everything that I get will be proportional to the result that just found times corrections of this order. If I discover that this overall coefficient itself is going to satisfy the condition that r dot over r omega is small, then I can continue this approximation. If it was large to begin with, then no. But you don't need to, I guess the point is that you don't need to actually do the full calculation with including r dot over r omega to get to this conclusion. You just need to keep track of the parametrics to see how would it depend on r dot over r omega, and then already in terms of parametrics, you see that whether it remains a good expansion parameter or not. One other thing that I can mention is that I didn't expect that much detail for this problem. So, I mainly wanted to know what I wanted you to see to derive the parametric dependence on the variable, which is basically this equation, regardless of these numbers. So that would be, for me, that would be satisfactory without 32 and 15, but with a minus. And this can be derived in a much faster way, because essentially we know that this Qij is m times Rij, or it's something of that order of magnitude. Then we take three derivatives of that. That would be something whose order of magnitude is Ri dot times Rj double dot. And then for this, we can use the fact that this R dot is a velocity, so I can call it omega r. And R double dot is acceleration, so it will be m son divided by r squared. And then we can use Kepler's law to relate omega to r. So for the power, we get something. Again, I ignore all of the numbers because I only wanted the parametric. So it will be g times the square of this thing, which will be g squared, ms squared, me squared, omega squared divided by r squared. So this is g cubed. And then omega squared from the Kepler's law is related to gm over r cubed. So this gives me g to the fourth ms cubed me squared this is for the power, and then for the energy, I think we already have it here. No. Also, this is the energy. E is minus G m sun ms divided by r. Therefore, E dot is G ms me divided by r squared r dot. So if I equate the two, I get this parametrics without the numerical factors. So in general, when I ask you to estimate, you don't need to worry about numerical factors. The signs are important because we want the radius to shrink, not to expand.
But can you just agree on that part that Qij is proportional to just that we had a delta function minus that thing? Why didn't you calculate that?
Well, I'm just keeping one characteristic, one typical term in Qij. So you could worry that if I keep the other term, that gives me a contribution which is much larger than, parametrically larger than what I have kept. So if what I ignore is parametrically larger than what I kept, that would be a disaster.
Yes.
So that I shouldn't do. However, it's not the case here.
How would I know it?
Well, you can just look at the other thing. It will be something of the same order.
Okay.
I mean, what is the other thing is like delta ij times r squared. So take three derivatives of that. It will be by r times three derivatives of another r, and r dot, r double dot. So you can just easily check. This is something easy to check whether two terms are of the same order parametrically or they are different.
Yes.
If they are parametrically of the same order, then you just keep one of them. You don't need to.
Yes.
I mean, for estimating, you can just keep one of them because we are not keeping the numerical coefficients anyway.
I see.
But keeping that would change, I don't know, 1 to 1/2 or 2.
Yes, because they are the same order.
Mm-hmm.
Yes, okay. So nice.
Yeah, one should be worried about this sort of cancellation. So it's always the risk of doing estimates. If there might be some physical reason that something cancels to 0, for instance. So if I ignoring two terms which are of the same order,
yes,
you might be worried that they cancel to 0. But in this case, that is also not, wouldn't be the case. Well, essentially because, I mean, the quadrupole of, there is no physical reason for the quadrupole of the system to vanish or to be time independent. There's no symmetry that protects that. Like the dipole is 0 because of the symmetry, because of the translational invariant. And the monopole is 0 because of energy conservation. But the quadrupole is not protected by any symmetry, so you don't need to worry much about it being 0. Okay, so I guess we don't have time for problem 3 and 4. Nevertheless, they are very important problems. So, what can we do about them?
We can do an extra meeting, maybe.
Yeah, or maybe we can. Yeah, let me think. Either we do them in class next Tuesday.
We have a vacancy in Monday or Tuesday, right?
You have one?
I mean, there was a tutorial that was cancelled, so for QFT. So there is a time
At
slot.
what time?
At 11.
Sorry, on Tuesday.
Tuesday? Oh, actually, I wanted to move the class to 11 on Tuesday because.
Okay, but it's just that.
But if you want, we can do it on Monday as well, maybe. If it's just for 3 and 4.
But anyway, I want to move the class, Tuesday class to 11 because there is a seminar in the afternoon. So that we will do. About the makeup session, let me think, then I'll email you. Maybe we just do this in class, or I do something about it.
Yes.
Not done it.
You didn't give us the last homework.
Was I so stupid in the board?
Yeah, me too, yes. You just can't figure this stuff in here.
I don't know what happened, man. I mean, okay, the clock is running fast.
When you go
It
home,
happens, yeah.
you go home. Not yet. Or do you want to spend some time?